So this will be, of course, the last ETSF online seminar of 2021. Many more to come next year, of course. So we're happy to have Stefano Di Sabatino from Toulouse University, who was supposed already to give a talk, the talk two weeks ago. Unfortunately, he was not feeling so well, so we postponed to today. And so Stefano will talk about photoemission spectra from the extended Koopman's theorem. So please, Stefano, go ahead.
Okay, so hello everybody, and let me thanks the organizers for inviting me to give this seminar. So the topic will be actually the how to obtain photoemission spectra from the extended Koopman's theorem. So let me start with some motivation. So why are we interested in photoemission spectroscopy? Because it's a powerful tool to get insight into the electronic structure and excitations in materials. So here on the left, you see a sketch of a typical direct photoemission experiment where light comes in and the electrons are kicked out, while on the right, you have an inverse photoemission experiment where electrons come in and light comes out. And in this way, we can probe the electronic structure of the system of interest. So on the other side, we have theory, which is an essential tool for the interpretation of experiments and to make predictions about material properties. And one of the most popular ab initio approaches is many-body perturbation in condensed matter physics, is many-body perturbation theory based on Green's functions. So the experimental spectra can be compared with the spectral function, which is directly related to the one-body Green's function.
Stefano,
yeah,
people would like to see your face. I don't know if your connection allows.
Probably I will have some problem with the connection. Okay.
Okay, just see what you think is best. Otherwise, we save your face for the questions. Okay, see what you think is best.
Yeah, I think I will leave for the questions because I don't have a very good connection. Okay. Okay, so and within the so-called GW approximation to electrocorrelation, many-body perturbation theory has become the method of choice for the calculation of quasi-particle band structure and the photoemission spectra for many kind of class of materials. However, GW suffers of some fundamental shortcomings, and in particular is not able to correctly describe strong correlation unless one introduces some sort of symmetry breaking in the system. This is the example of many paramagnetic insulators which are not correctly described by GW. So a typical example is nickel oxide. As you can see on the left, GW is able to correctly describe the insulating nature of this phase, or the antiferromagnetic phase. However, the real challenge is to open a gap without any symmetry breaking, as it should be the case of the paramagnetic phase, which here I'm reporting on the right. In this case, the band gap opening is purely due to strong correlation, which GW is not able to correctly describe. So this motivated us to explore alternative ways to calculate the spectral function, and in the following, I will present a method that allows to overcome this kind of problems. So this is the outline of the talk. First, I will introduce the basic ideas of the extended Koopman's theorem. Then I will show you how to combine the EKT with the reduced density matrix functional theory. So I will start introducing some basic equations, and then I will test the performance of this approach, first with some simple models, and then in more realistic situations. And finally, I will draw some conclusions and present some outlooks. So let's start with the extended Koopman's theorem. So the EKT has been derived independently by Day and Morrell, basically in the framework of quantum chemistry, to calculate charged excitations. And basically, we start considering an electron system in its ground state. And then for the n-1 electron wave function, we make this kind of ansatz. So basically, in second quantization form, we have these ansatz, where OV is a destruction operator corresponding to the orbital 5e. So basically, what we are doing is to remove one electron from the n-electron system in this particular orbital. And this orbital will be determined later variationally. So the removal energy can be expressed in this way as a difference of expectation values of the Hamiltonian. And if we use these ansatz for the wave function of the n-1 electron system, we obtain this expression. And one can show that this difference can be written in a more compact form in this way, in terms of this commutator between the Hamiltonian and the destruction operator of V. Then, in practice, we introduce a set of new orbitals, phi I, in such a way that the destruction operator of V can be written as a linear combination of this new set of orbitals, operators, and in terms of this linear coefficient C. So we introduce this expression for OV in the removal energy, and then we impose the stationarity of the energy with respect to the coefficient C. So we end up with this generalized eigenvalue problem in terms of these two matrices, S, which correspond to the one-body reduced density matrix, gamma, defined in this way, and F is the so-called generalized Fock matrix, which is expressed in terms of this commutator. So from the solution of this eigenvalue problem, we obtain the approximate removal energies of the system. So what we have to do is to find an approximation or a way to calculate these two matrices. And this can be done within different theoretical frameworks. For example, it can be done within quantum Monte Carlo or using configuration interaction methods, or also using reduced density matrix functional theory. These are just examples. And later I will show two examples to do this. Then one can do something similar for the addition part. So doing this kind of ansatz for the wave function of the n+1 electron system, we are just adding one electron in this orbital phi C. So this will be the corresponding addition energy. And imposing the stationarity of this energy, we end up with this generalized eigenvalue problem, where now S is given by this expression, and basically is 1 minus the one-body reduced density matrix, and the generalized Fock matrix is given by this expression. So from the solution of this problem, we obtain the approximate addition energies of the system. So just to summarize, what is the physical picture behind the extended Koopman's theorem? So we start doing a quasi-particle-like ansatz for the n-1 and n+1 particle wave functions, just removing or adding one electron. And we use these approximate wave functions to calculate removal and addition energies. So in doing this, we include correlation in the formulation. In fact, these approximate wave functions will not be, in general, single Slater determinants. So we are taking into account for the correlation, but we are neglecting the relaxation of all the other electrons after the removal or the addition of the test electron. So this kind of relaxation can be important in small systems like molecules. However, we expect it to be far less important for extended systems, so the kind of system we are interested in. So basically, the extended Koopman's theorem has been used in literature to calculate charge excitation, so which means ionization potential and electron affinities for molecules, while there are really few examples of the use of the EKT for solids. So this is one of the few examples that we found in literature. This is taken from Kent and co-workers. Basically, they combined the EKT with the quantum Monte Carlo to calculate valence and conduction band energies of bulk silicon. So these are the results. On the right, you have the full, the complete band structure, while on the left, just a zoom of the band gap region. So the EKT at QMC results are reported with these squares and circles. And I am also reporting with this solid black line, the empirical set of empirical pseudopotential data. We are in good agreement with the experiment, so they will serve as a reference for the QMC results. So as you can see globally, here we see that the band structure is quite well reproduced. We have just a slight overestimation of the band gap between these 2 points, which is about, the overestimation is about 10% of the experimental value. And also we have also a slight overestimation of the valence bandwidth, but globally we have a quite good description of this, the band structure. So this is what we can obtain combining EKT and QMC. However, QMC has some problems, and for example, from a computational point of view, can be quite expensive. So in the following, so we decided to follow a different strategy, that is to combine the EKT with the reduced density matrix functional theory, whose the working quantities are reduced density matrices. So the first step is to express the EKT equations in terms of reduced density matrices. So this is so let's first focus on the removal part alone. So we start defining this new matrix lambda in terms of the matrices S and the generalized Fock matrix that I introduced before. Then we choose to work in the basis of natural orbitals. So this choice is quite natural for when we have to deal with the reduced density matrices. In fact, the natural orbitals are the eigenfunctions of the one-body reduced density matrix, and the corresponding eigenvalues are the so-called occupation numbers, which are given by this Ni. So then we take the expression for the generalized Fock matrix, and we work out the commutator inside here using this expression in second quantization for the Hamiltonian. And what we obtain at the end is this expression for lambda r. So this lambda r is a function, is expressed in terms of occupation numbers, which means in terms of the one-body reduced density matrix, and in terms of this gamma 2. Gamma 2 is the so-called two-body reduced density matrix, which is defined here in this way. Something similar can be done also for the addition part, and we will obtain this other expression, still in terms of occupation numbers and the two-body reduced density matrix. So the eigenvalues of these two matrices are the approximate removal and addition energies of the system. So what we need to do now is to find good approximations, a way to calculate these the one-body and two-body reduced density matrices. So a way of doing this is offered by reduced density matrix functional theory. So here in this slide, I will present the basic concept of this theory. So the spirit is quite similar to density functional theory, but now the basic variable is the one-body reduced density matrix gamma. So, and in fact, thanks to a one-to-one mapping between gamma and the ground state wave function, all the ground state properties can be expressed in terms of gamma. And in particular, the total energy functional is given here, and is a sum of a kinetic term, a term due to the coupling with an external potential, the R3, and the so-called exchange correlation term. And in particular, the exchange correlation part is directly related to the exchange correlation part of the two-body reduced density matrix, where V is the Coulomb potential. So the solution of this problem, which means the exact one-body reduced density matrix, is obtained by minimizing this total energy functional, with imposing some also imposing some extra constraints for the representability of gamma. However, the exchange correlation part is not known. So in general, it's not known. So we need to introduce some approximation. And in the following, I will focus on this approximation, a so-called power functional, which was introduced by Sharma and co-workers. Basically, it can be seen as a modification of the R3 Fock approximation, where we introduce this parameter alpha to take into account for the correlation. And alpha is in the range 0.5 and 1. And in particular, for alpha equal 1, we obtain back the R3 Fock approximation. Then, in practice, one introduced the spectral representation on gamma in terms of occupation numbers and natural orbitals. So the minimization of the total energy can be performed with respect to n and phi, with these extra constraints on the occupation numbers. And from the optimal occupation numbers and natural orbitals, we can build back the one-body and two-body reduced density matrices, which are used as ingredients of the EKT expressions to obtain removal and addition energies. So now let's see how this method, this approach performs in practice. So first, I will consider the case of a simple model. So this is the we consider the one-dimensional Hubbard model at 1/2 filling. So here I'm considering the case of when the ratio between the on-site interaction and the kinetic term is equal to 4. So this should correspond to a moderately strong correlation regime. And here I'm reporting the exact band gap as a function of the number of sites in the model, in the Hubbard model. So in black and in blue, instead, are the results obtained with the EKT formulation combined with the exact, using the exact reduced density matrices as ingredients. So we see that except for the L equal 2 for the dimer, we obtain the exact result. In general, we have an overestimation of the band gap. And this overestimation is a general trend that we observed in the EKT. And this can be understood looking directly at the EKT equations. So let's first focus on the removal part. So this is the expression for the removal energy that I gave you before. So what we do is to insert a complete set of eigenstates of the n-1 electron system here. So, and from the action of the Hamiltonian on the left and then on the right, we obtain this expression where these energy differences are the exact removal energies of the system. Instead, these terms here, which appears in the numerator and the denominator, are the so-called Lyman amplitudes, which basically are related to the intensities of these removal energies in the spectral functions. So they are the intensities of the peaks of the spectral function. So we see from this relation that basically the approximate removal energy is a weighted average of the exact removal energies of the system. So to illustrate what happens in practice, let's consider this simple sketch for the exact spectral function. So we have one quasi-particle peak on the right and a series of satellites on the left. So the EKT will produce only one peak, so one removal energy, whose position is the average of the position of all these structures in the exact spectral function. So this means that this the approximate quasi-particle is redshifted with respect to the exact one. Something similar happens for the conduction part, so for the addition part. But in this case, the approximate the EKT will give an approximate quasi-particle which is blue shifted with respect to the exact one. So this produces an overestimation of the band gap. However, this overestimation can be compensated when we introduce the extra approximation on the ingredients of the EKT, so on the approximation on the reduced density matrices. So for example, these are the results obtained with the EKT together with the power functional with alpha equal 0.5. So in red, we are basically on average, we are very close to the EKT with exact reduced density matrices. So this shows that this functional, at least for the Hubbard model, is quite good. And when we increase the value of alpha to 0.6, we see that we decrease the band gap. So this means that we are closer to the exact band gap, but this is simply due to a compensation of error between the two levels of approximation that we are using. So one is the fact that the EKT is an approximate method, and the other is that we are using approximate ingredients inside the EKT. So these are the results for the Hubbard. Then here I'm considering another simple model, the homogeneous electron gas, which should capture the basic physics of simple metals. So here I'm reporting the valence and conduction energies, so the removal and addition energies of within the R3 Fock approximation. So on the right, you have a zoom of the valence part only. So this is what is obtained within one-shot GW. So we have a smaller bandwidth with GW. And these are results obtained by Krogel and co-workers combining the EKT with the quantum Monte Carlo. So unfortunately, these results are available only for the valence part. So we don't know anything about the conduction part. And these results are will serve as a reference for our next for our calculations. So this is what one can obtain. Imagine to using the best reduced density matrix inside the EKT. So when we combine the EKT with the power functional, still with alpha equals 0.5, we obtain this red curve. So the most striking feature is the presence of this unphysical band gap that you can see here on the left. And when we focus on the valence, we see that basically we are on top of the Artifock result up to a certain value of the momentum, and then we have a sort of deformation here, close to the Fermi momentum. If we increase the value of alpha to 0.6, here we see that we tend to close the band gap. However, for the valence, we are still too close to Artifock. So this means that with this kind of functional, the best result that we can obtain is Artifock for alpha equal 1. So this clearly shows that something is missing in these functionals, in this kind of functionals. And one would say that intuitively, what is missing is a sort of screening. So this is why. So this motivated us to introduce the screening in the formulation. And in the following, I will show you how to do this. Basically, we exploit the link between reduced density matrices and Green's function to export approximation to the commonly used approximation to the self-energy to approximation for gamma 2. So in particular, we exploited these two relations. So this is the link between the one-body reduced density matrix and the one-body Green's function, and two-body reduced density matrix and G2, the two-body Green's function. Basically, one has to take the equal time limit in the Green's function with a proper time ordering to obtain the corresponding reduced density matrix. Then we considered this relation linking the two-body Green's function to the self-energy. So then we have to take the equal time limit on both sides with the proper time ordering in such a way that on the left we obtain the two-body reduced density matrix, which is now expressed in terms of the self-energy. Then we introduce an approximation for the self-energy. In our case, we choose the GW approximation with a static screening, so the screen exchange approximation. So this is the expression for the exchange correlation part of sigma in terms of this static W bar, so this static interaction. When we plug this expression in this equation for gamma 2, what we obtain is this. And here we notice that we have the equal time limit in the Green's function with the correct time ordering. So which means that here we have the one-body reduced density matrix. So basically, this is a functional for the exchange correlation part of the two-body reduced density matrix in terms of gamma only. So here we notice that W bar is not a functional of gamma. In fact, in our approach, we fix at the beginning this W bar. So for example, it can be obtained within the RPA approximation, starting from G0 for the non-interacting Green's function, and we keep this quantity fixed starting from the beginning. Then we insert this approximation in the energy functional. We minimize the energy functional, and from the output, we build the EKT expressions with this same approximation to calculate removal and addition energies. So we introduce also another modification of this functional. So in the same spirit of the power function, what we do is to insert this parameter alpha here, and this will be we call this approximation screened power functional. So part of the correlation will be taken into account by the presence of the parameter alpha, and part of the correlation by the presence of the screening here in the interaction. So what can we obtain with this kind of approximation for the homogeneous electron gas? These are the results. You see in blue, the EKT is combined with the WPF with the alpha equal to 0.5. So we tend to close the band gap. But the interesting point is that for the valence, here we obtain a result which is quite close to the GW result. So we have an improvement in this part. However, we deduce that this improvement is simply due to a compensation of error because our reference, the AKT with QMC, is here. So this difference between our results and the QMC results are due to a compensation of error. So these are the results for the valence and conduction energies. But the EKT offers also a way to build approximation for the spectral function. So here I will not give you the derivation of this. I just want to give you the final expression that can be obtained. So the spectral function is as this form, so in terms of Dirac delta functions, where these energies are the EKT removal and addition energies, and the intensities are related to the occupation numbers. So for example, for the homogeneous electron gas, this is what we obtain for the momentum resolved spectral function. On the left, you have the EKT combined with the power functional, and on the right, combined with the WPF. So we see that we have a global better agreement with the GW, which is reported with this dashed white line. However, yes, also we notice that we have this unphysical band gap in both approximation. However, here for the WPF is smaller. So this is what we can obtain. We obtain for models. So models are very useful because you can benchmark the different level of approximation that are involved. But what happens in a more realistic situation? So this is again the case of silicon. So here I'm reporting again the EKT at QMC results and the empirical pseudopotential data with a continuous line. To obtain our results, we implemented our approach in a modified version of the L code. And this is what we obtain in red when we combine the EKT with the power functional, the standard power functional. So using a value of alpha equal to 0.65. So this is the value that is suggested in literature for solids, for this kind of system. So we see, looking at the results, that we have a large overestimation of the band gap, which is about 7 times larger than the experimental one. And we also have an overestimation, general overestimation of the valence bandwidth. When we introduce the screening in the formulation, instead we have these blue dots. Basically, we are really close to the EKT at QMC results, so which means that we tend to close the band gap, which is now very close to the experimental one. So this is what happens for this simple system. But what happens when we consider a more challenging case? So here I'm considering again nickel oxide. So I'm reporting the experimental spectra for both the antiferromagnetic and paramagnetic phases. We notice that they are very similar. And the results of our calculation are reported with this blue line. So first we notice that we open a gap for both phases. So what is important to stress is that we open the gap also in the paramagnetic phase, so in absence of any symmetry breaking in the system. So this is the typical situation where other standard ab initio methods like GW fail. Instead, we obtain a good description, qualitative good description of the paramagnetic phase. However, this band gap is overestimated in both cases. So we obtain a value between 15 and 20 electron volts, which has to be compared with 4.3, the experimental value of 4.3 electron volts. So we have this overestimation, but we can say that qualitatively we obtain a the description of this material is not, this kind of systems is not so bad. And in fact, if you look at the valence only, we see that we have also a good description of this part of the spectrum. So as I said before, the results for both phases with our approach is quite similar. However, the physics behind the opening of the gap is quite different for these two phases. And this can be seen looking at the distribution of the occupation numbers, which is reported here with these two color maps. For the antiferromagnetic phase, we see that the band gap opens between states whose occupation numbers are close to 1 and 0, while for the paramagnetic phase, we have an important contribution also from occupation states with occupation numbers around 0.5. So this is a typical situation where quasi-degeneracy appears, and where one has to explicitly take into account for electron correlation to correctly describe the material. And this is the situation, as I said before, where GW or other standard ab initio methods fail, while our method is able to capture the physics of the system. So this slide is just to stress on the fact that the qualitative picture that we get is correct. So here I'm comparing for nickel oxide, the paramagnetic phase of nickel oxide, the EKT band structure in blue with some experiments here. So we have a quite good agreement. So the only problem is the overestimation of the band gap. Then this figure is just to say that we obtain similar trends also for other transition metal oxides. So you see manganese, iron, cobalt oxide, and again nickel oxide. And here I'm also reporting the composition of the spectral function that we obtain with our method, and the composition with respect to transition metal D states and oxygen states. So also in this case, we found that the picture that we obtain is qualitatively correct, if compared with other methods like dynamical mean field theory, which are designed to describe strongly correlated systems. So the only problem that we have is this overestimation of the band gap. So can we do better introducing the screening? So we see that, again, these are the results of the EKT with the standard PF. And when we introduce the screening, we reduce the band gap. So now we are closer to the experimental one. However, we lose a bit on the quality of some feature of the spectral function. In particular, we widen too much the valence part here. And also we observed that the ordering of the conduction band is not correct anymore introducing this screening. So we suspected that this problem is due to the fact that orbitals with different natures in this material, so orbitals with S, P, and P nature and the more localized d orbitals behave in a different way when we introduce the screening. So this is a point that we are still studying in more details. So this is still a work in progress. So to summarize, I presented the extended Koopman's theorem as a promising tool to calculate photoemission spectra for solids. This in principle can be done within different theoretical frameworks, but here I focused on the combination of the EKT with the reduced density matrix functional theory, and I show you how removal and addition energies can be obtained from the one-body and two-body reduced density matrices. So I tested this approach first considering simple models, and in particular for the homogeneous electron gas, which should capture the physics, the basic physics of simple metals. We found a qualitatively wrong picture description. I mean, in fact, for the presence of this unphysical band gap, while considering gapped material like silicon and transition metal oxide, we obtained a qualitative good description. However, we observed this large overestimation of the band gap. So this overestimation can be cured introducing the screening in the formulation. So I show you how for silicon we obtain quite good result, while for a system like transition metal oxides, we have a reduction of the band gap, but still there are still some points to be fixed. So possible ways of improvements. So as I said before, we are currently trying to understand how to properly introduce the screening in the formulation to take into account for the fact that orbitals with different nature respond in a different way to the screening. Then another possibility would be to extend more advanced reduced density matrix functional, which are originally designed for molecules. For example, the so-called Phys functionals, and which has been shown to perform very well for this kind of molecular systems, and try to extend them to bulk to solids. Another possibility would be also to explore the performance of higher order correction to the extended Koopman theorem. This can be done simply introducing higher order excitations in the ansatz, the starting ansatz for the EKT. For example, considering 2-hole 1 particle and 2 particle 1 hole excitation in the ansatz. So in this way, one expects to better reproduce the position of the quasi-particle, but also to describe satellites. And of course, it will be interesting to do this within the framework of reduced density matrix functional theory. And another interesting point would be to produce a set of reference calculations, for example, obtained combining the EKT with quantum Monte Carlo. I mean, to have a reference to compare with the outcome of the 3 previous points. So as I show you, basically in literature, there is only one calculation made for silicon, combining the EKT and quantum Monte Carlo. And it would be really interesting to have, I mean, the same kind of calculation also for strongly correlated materials like nickel oxide. So, and before to finish, I would like to thank all the people who have participated to this project at different stages. And also I would like to thank you for your attention. Thanks.
Thank you very much, Stefano, for this nice talk. So the floor is open for questions. So please, go to the reactions and raise your hand if you want to ask a question. So I see a question from Rex. Please go ahead.
Yes, Stefano, you mentioned near the start of your talk that in using any RDM functional theory, you have to constrain the RDM to correspond to an appropriate many particle wave function. Were you doing that in this case? And where does that actually come into the theory?
Okay, so it comes simply when you have to minimize your functional. So it's here. So when you have to minimize your total energy functional, so you have to impose that during the minimization, so your one body reduced density matrix is correspond to the wave function of an electron system. So basically what you do, you translate these representability conditions in terms of occupation numbers and also natural orbitals. So basically that kind of constraint that you have to impose is that the occupation number for a particular orbital is between 0 and 1. Basically this is related to the Pauli exclusion principle, and then the sum of the occupation numbers is equal to the total number of electrons. Of course, you have also to impose that your natural orbitals are orthogonal. So here, in fact, there is one condition missing. And so when you minimize your energy function, you always have to keep in mind this constraint.
So you were imposing those constraints then?
Yeah, yes, you have to impose these constraints.
Okay, there's a question from Trond.
Yes, so in the extended Koopman theorem, you have some equation with the generalized Fock matrix. And for instance, for the removal, you multiply with the inverse overlap. So you have inverse occupation numbers. Can that lead to instabilities for low occupancy?
Yes, of course, you have to be sure that you can invert this matrix. I mean, in principle, I mean, a condition for the invertibility of this matrix that you don't have occupation numbers equal to 0. This is actually in practical situation, you never have occupation numbers equal to 0. But anyway, in practice, yes, you can have instabilities. So these, in general, what you do is to solve with
so
other
just
kind of
a
methods.
parenthesis, I mean, with increasing static correlation, you should expect to have some at least low occupation numbers. I mean, when it's not a clean separation.
So what is done in practice is to solve this kind of problem, the generalized eigenvalue problem, with other methods. So you don't really invert this matrix in this way. So we used this approach just to derive some equations. And in our situation, when we use the reduced density matrix functional theory, I mean, you can have instabilities. And for example, in the results for the homogeneous electron gas kind of instability, so when the occupation numbers are close to 0, are these kind of tails that you obtain. But in our case, basically, it's not a big problem because when we calculate this, then the spectral function, so they are weighted with the corresponding occupation numbers. Then in the final result, you don't see so much this kind of tails.
Okay, so just quickly, another quick question. So for the Hubbard model, you explain possible shortcomings or problems with the extended Koopman theorem. And you show these peaks. I mean, you have like several peaks, and with EKT, you have like a single one, this one picture, yes.
Yeah.
But I mean, when you solve this equation, you get several solutions, don't you? So you get several removal energies to the left.
Okay, yes. So this, I mean, I forgot to stress on the fact that this refers to a single component of the spectral function. So you take only one component of the spectral function. So you project on a particular orbital. So you have the corresponding spectral function. In that case, you have one energy for the removal part and one energy for the addition part. So then to obtain the complete spectral function, you have to sum. But all the components, for all the components of the spectral function, you have this kind of overestimation. So the overestimation is valid also for the total spectral function. So this is why we have only one peak for the EKT, because you are considering only one component.
Okay, so now it's clear. Thank you.
Yeah.
I take advantage since you are showing this picture. So in the Outlook, you mentioned indeed an interesting way to go to improve on the AKT by including like the satellites, by including 2 hole 1 electron or 2 electron 1 hole. So yeah, I can see that then you get also the satellite energies, but it's not clear to me is how that then would improve the quasi-particle energies, because it seems that EKT, you just do one calculation, you get the quasi-particle energy. How can you then improve? You have to somehow recalculate them by doing sort of a weighted average. I'm not sure if my question is clear.
Yes, it's clear. So in fact, I have a slide for this. So basically what you do in the for example, the next level of theory of the EKT is the so-called EKT tree. So basically in the ansatz, you are considering one particle 2 hole and 1 hole 2 particle. So basically when you use these ansatz and derive all the EKT tree equations, what you see is that you can obtain the quasi-particle, but also some addition extra energies, which are supposed to be the satellites. So the fact that when you consider, for example, related to your question, you have this figure on the right, where you have just one main quasi-particle in the exact spectral function, so in black. Basically, the fact that in your spectral function you have some satellites, so this will tend to move the approximate EKT energy a bit far away from the quasi-particle. So this is the effect of the fact that in doing these averages, you have also the satellites. But when we do the second order of the EKT, I mean the EKT3, so you will have two energies. And this means that in the energy which correspond to your quasi-particle, basically the effect of the satellites is less strong. So we'll try to better reproduce also the position, better reproduce the position of the quasi-particle. So I don't know if I was quite clear.
Okay, so also the EKT that you have for the quasi-particles, the equation that you showed at the beginning, will be modified.
I mean, no, when you consider the EKT3 as output of the EKT3, you have obtained the quasi-particle and satellites. So which means that you don't have to do again the EKT1, the first order of the EKT1. So you forget about the EKT1, you pass directly to the EKT3, which will give the quasi-particle and satellites.
Okay, and so it's okay. Because you have that equation? Do you get a similar equation where you just have the energy of the quasi-particle or quasi-particle and or satellite equal to some expectation value involving commutators of the Hamiltonian?
Yeah.
Okay.
So now in this case, you obtain another generalized eigenvalue problem.
Okay.
Whose solutions are the quasi-particles and satellites. So you have everything inside this new formulation. So you don't have to consider again the EKT1, the first order of the EKT. So you will get everything directly from the EKT3.
Okay, clear. Let's see. So Tron, did you have another question, or you kept your hand up?
I'm sorry, I have to take it down.
Okay. So let's see. I don't see any further questions. So last chance, I would say. Okay, if not, okay. Thanks again, Stefano, for this nice talk. And well, happy holidays to everybody. And I think we'll be back at the end of January for the next ETSF seminar. Bye, everybody.